Suppose f from AB to R is a function. We want to understand if f is integrable or not. We already know that f will be integrable if for each epsilon greater than 0 we can find a partition. We can find a partition P such that u of fp minus L of fp is less than epsilon. Now, from the way in which these upper sums and lower sums are defined, it is clear that this quantity u of fp minus L of fp will be less than epsilon if and only if on each subinterval determined by the partition, the variation of the function f is very small. In other words, if you just rewrite this as capital Mi minus small mi delta xi, we want this quantity to be small. We want this quantity to be small. If this quantity is always large, then it doesn't seem like it would be possible to make this entire summation capital Mi minus small mi delta xi to be small. Okay, so the one reasonable intuition behind what an integrable function is that the variation in the function in subintervals is not too large. Now this is seen clearly when we showed that any continuous function will automatically be Riemann integrable. Continuous functions behave very well if you make these partitions, thus each interval in a partition really small, then it is reasonable to believe that capital Mi minus small mi can be made very, very small, and this was captured by using uniform continuity in the proof. Now, we want to see whether there are other functions apart from continuous functions that are Riemann integrable. In other words, we want to see functions for which this variation capital Mi minus small mi is not too large. So what we are going to see eventually in the next few modules is that the precise condition under which f would be integrable is if the set of discontinuities, or in other words the set of points where the oscillation of the function f is greater than 0, if that set is small, then the function will be Riemann integrable. So let me write that down. The intuition is that if the set of discontinuities, that is the bad points, set of discontinuities d of the function f, if small, will imply f is integrable, and vice versa. This is something that is palatable. Now, the only problem is this small that I have written should actually be in quotes, because what exactly is a small set? There's a precise technical condition called being a set of measure 0 that captures this definition. This is the definition of set of measure 0. This will intuitively capture the fact that a set S is a small set. Let S subset of R, we say S is a set of measure 0 if for each epsilon greater than 0 we can find an open cover, rather a countable open cover, comprising open intervals. Let's call this some fancy O. This is just a collection of open intervals ai, bi, such that I comes from the natural numbers. So for each epsilon greater than 0, we can find a countable open cover comprising open intervals such that the net length, summation bi minus ai is less than epsilon. Okay, so a set is a set of measure 0 if you can do this for each epsilon greater than 0. That means in some sense the net length of this interval is smaller than any given epsilon. Therefore the net length of this interval, which we use the more technical term measure, the net measure of this of this set S, the net measure of this set S can be made less than any given epsilon. Therefore it is sort of like having no measure at all. It's a set of measure 0. It's a small set. So this is a technical concept, so it's good to see examples, and many of them. Examples. Any finite set is a set of measure 0. What I will do is, I will keep making these examples more and more complicated. It will turn out that I think the final example will subsume everything else, but it's a good idea to progress this way. Any finite set is a set of measure 0. How do you see this? Well, you enumerate the points as x1 to xn and just consider x1 minus epsilon by n, x1 plus epsilon by n. This as one of the elements of the cover, and x2 minus epsilon by n, comma x2 plus epsilon by n, dot dot dot, xn minus epsilon by n, xn plus epsilon by n. Okay. Now the way I have done it, you will get an additional factor of 2, but I want you to check that the net length, so let me put this as the set O. The net length of the intervals in O is less than 2 epsilon, I believe. Okay. Please check this. So that really doesn't matter. The factor of 2 really doesn't matter. So any finite set, I can just look at this finite set and keep making these covers, these open intervals around this finite set smaller and smaller to make sure that the net sum is less than epsilon. This can always be done. So any finite set is automatically going to be a set of measure 0. Enhancing this, any countable set. So let me call this 2, let me call this 1. Any countable set is a set of measure 0. This is also not too hard to see. What you do is you enumerate this as x1, x2, dot dot dot, so on. You'll make it the list. Because it's a countable set, you can list it. Now the problem is there is no factor of n in the denominator that you could do to normalize it. Well, that really doesn't matter. We are now experts in convergence series. What you do is you consider the collection O defined to be the open interval xi minus 1 by 2 power n, epsilon by 2 power n, comma xi plus epsilon by 2 power n as I runs through the natural numbers. You look at intervals of this type. So what is happening is, since we have no control over the denominator, we cannot have an epsilon by n. What you do is you start shrinking subsequent things. So if this is x1, this is x2, this is x3, you make the intervals smaller and smaller, and you control the size of these intervals by putting this 2 power n in the denominator. We already know what summation 1 by 2 power n is, and check again that net length of the intervals in O is less than 2 epsilon, I believe. Okay, please check this in detail. So this trick is very, very useful. It will be used many, many times. Whenever you have some countable object and you want to control it, you put a epsilon by 2 power n factor somewhere, and that will allow us to control the sizes. Excellent. The third example is now rather obvious. Any subset of a set of measure 0 is also a set of measure 0. This is fairly obvious because what you do is, given an epsilon, you just consider the corresponding cover O for the larger set. The same thing will be a cover for the smaller set. So this will work. Fourth example, I want you to work out on your own. Show that any countable union of measure 0 sets is measure 0. If you take small sets and take countably many of them, you will still get back a small set. Let me give you a hint. So you have to fix epsilon greater than 0 and produce a cover of the union, right? What you do is you produce a open cover for each set in this union. For the first set, you make the net length less than epsilon by 2. For the second set, you make it less than epsilon by 4. For the third set, you make it less than epsilon by 8. You see where this is going? This is exactly like the countable set case. In fact, this example subsumes the countable set case. Okay, so fix epsilon by 0 and cover the set AI. So any countable union of measure 0 sets AI is measure 0. So cover the set AI with an open cover of net length less than epsilon by 2 power I. This will give you the desired result. Okay, so this is just elaborating the details. The key idea is already subsumed in the proof of countable set is going to be a set of measure 0. Another exercise for you, show that the Cantor set is a set of measure 0. Okay, so recall that the Cantor set is uncountable. So this sort of says that don't be misled into thinking that only countable sets are going to be sets of measure 0. You have sets like the Cantor set which are also sets of measure 0. In this regard of the Cantor set, there's something interesting that's happening. We already saw that the net length of the intervals that were removed from 0, 1 is 1, right? We already saw that, so it is sort of expected that the Cantor set will be a set of measure 0. So the key thing is sets of measure 0, it's capturing the idea that a set is small. We are going to now show in the next module that a function is integrable if and only if the set of discontinuities is actually a set of measure 0. This is a course on real analysis and you have just watched the module on sets of measure 0.